Okay, so let's see. Those of you who were not there class before, I think it was Monday, Professor Pollack handed out these second lab description. So please pick them up, and I'll actually post it and on the website as well. And I hope you have gotten started with some of the design, and please contact him and take your design to him, and he'll discuss that with you, and then you basically will decide on a time to go in and make the laser for this lab. The second, or rather the first lab, I think all of you are have finished the lab, so I will suggest turning in your reports this Thursday, this week on Thursday, and I think a single report per group. So please work together and submit it to me. Yep.
You said the due date was Tuesday. So
did I say that?
yeah.
Great.
On the 10th you posted.
Okay then. So sorry. Yeah. Let's see. I mean, the way to look at it is the longer you take to write this up, the more you delay your lab too. So I think if you are done by Tuesday, please turn it in. That's absolutely great. Yeah. I mean, nobody's going to stop you for turning it in earlier. So, okay. So if I did say Tuesday, I'll check it. But turn it in by Thursday. I mean, it's a I think you have the data, you have to plot it, and there's, just write a coherent report on that. Okay, so actually Professor Pollack and I did discuss a little bit of what to do in the last 3 classes this week. And here's what we decided to kind of finish up the course with the following things. One is to give you an idea of what are the current applications of the lasers that we have discussed till now. We have discussed a lot about the physics of lasers and lately a bit about semiconductor lasers. Today we'll discuss a little bit about some of the details of the semiconductor laser, but more so about how do you design the laser aimed at a communication system, at a very high data rate communication system, for example, today, and digging down to the basics. What are the design parameters that typically you play with to make it possible? So the first, I want to give that an overview, or in some sense a survey of that, rather than getting too deep into any of the details. And the purpose of that is to kind of finish the course. This is a 4-level course, if you might. So our goal also is to give you a fair idea of what is it that we did not cover in the course. I mean, obviously, every topic has a certain degree of breadth and a certain degree of depth you can get into. But I want to, we decided it's also important to show you a couple of things that we didn't get too deep into, but there are still current areas of research. There are a lot of open questions, and I want to kind of show those to you as well by digging into the what are the I shouldn't say completely not understood phenomena, but what are the things that still need quite a bit of work in terms of understanding in the fundamental aspects of such photonic phenomena. Okay? So we'll start with where we kind of ended in the last class. Essentially what we developed was a very engineering or a phenomenological approach for lasers, and that approach where we kind of did a rate equation for electrons and a rate equation for photons. So rate equation for electrons, so that I inject a certain amount of electrons into the active region, and some of them recombine by spontaneous emission process, and the rest recombined by stimulated emission process. And the stimulated emission part is proportional to the power that is in the radiation field or in the photons. And that part which is lost by electrons, I mean, you lose electrons to stimulated emission, is gained by photons. So that term appears here as a positive. This is the power in the photon field or the light field, and it appears here as a positive part. But then you also generate photons by spontaneous emission. Essentially, this also appears here. then you lose some from the cavity. That's your useful output power of a laser, for example. And by combining these two and solving it a steady state, you end up with the output power as a function of injection current that looks something like this. There's a threshold, and then above it you get an output power that's linear. You also saw this in your experiment in the first lab. The output power of the laser looks something like that. You have spontaneous emission, and then you kick in with the stimulated emission. Now, because you have the rate equations, you can also say that instead of a DC current, I inject an AC current with a certain frequency, then will the output power follow at that frequency? And that's the dynamics of a laser. So if I inject a AC or an oscillating current, what happens to the output power? Do the photon numbers or the output power in light also oscillate with time? And it does, except that it doesn't do that. There is a certain frequency limits to how fast you can do that. And that kind of is an expression that comes about again by feeding in the input current as e to the power j omega t, and tracking what is output power as a function of this frequency, and you get output power divided by the input current has a certain frequency response. And at very low frequencies, if you are below about a gigahertz, you are okay. The output power really follows the input current, but above that you have a resonance at a certain frequency, and then you have a decay, and then if you try to do it too fast, it doesn't quite follow. The output power doesn't follow the input current. So that's a theoretical model, this particularly is a phenomenological model. How does it look in a real laser? For example, if you pick up a semiconductor laser, here's a laser diode as an example. It could be edge emitting, it could be surface emitting, and then you have your gain medium, you have your mirrors. Typically, if you want to select a certain frequency, you have what you call the name would be a mode selection filter. It could be one of these Fabry-Perot or something that you put in. In a semiconductor, it's basically just an edged mesa that does that job for you in the process. And based on the gain medium, you have your whole gain spectrum. You calculated that in your last assignment, the gain spectrum of a semiconductor gain structure, which either could be a bulk p-n junction, or it could be quantum wells or quantum wires, whatever be it. So you have a gain spectrum that may look like this as a function of frequency or wavelength. Here it's plotted as a function of wavelength. And based on the cavity size, right, the size of the mirrors and the cavity, you have your FSR, which is all these lines here are allowed modes, cavity modes. So this is something we've been discussing through the whole semester, right? And then by choosing maybe a Etalon or quite a few other designs as well, you can select out a particular mode. It's a mode selection filter, and kind of reject all the others. So that's the idea. And then you get a single mode lasing with a semiconductor laser, and then the output power versus current would look like that. Here's experimental data, output power versus injection current. You are generating one in your current, lab one as well. So that's the couple of other things that happen till here. You have spontaneous emission. If you take this and plot it in a log scale, that's how it looks. Logarithmically, you still have output power at very low currents below threshold, but that's spontaneous emission. That's not coherent light. It's a LED sort of behavior. And then when you hit threshold, you have very sharp turn on, and then essentially it locks into this is the laser output now. This output is a laser with a certain slope, which is called the differential efficiency. And when that happens, your spontaneous emission or the carrier, the gain was increasing as you increase the gain. Remember, your gain starts out as loss when you do not inject any carriers, and then you inject more and more, pull the quasi-Fermi levels into the bands, and then you flip sign from negative to positive, and it becomes gain. Right? And then now the gain increases, and then at some point it actually clamps, and it doesn't increase any further beyond the threshold. Similarly, the carrier density increases, and then it clamps. Essentially, all it means is beyond the threshold of the laser, you still have spontaneous emission, but that's locked no more than what it was below the threshold. And the carrier density locks and all that, and the output power looks like that. So these are experimental data. Here's an experimental data of the frequency curve, how fast can you modulate, and then you can see that as you inject more current, you can kind of push it a bit to the right. That depends on the denominator, and then here you're kind of looking at the resonance and also the decay of this is, for example, a vertical cavity surface emitting laser or a VCSEL as an example, but all edge emitting lasers will also do that in general. Okay, so that's that as an example is semiconductor laser, and what I want to spend a few minutes talking about are some of the internal design parameters of the laser. So the gain spectrum we have already talked about. You design it by choosing the active region, quantum well size, thickness, material, and all that. That will design your gain spectrum for a semiconductor laser. For atomic laser, I think we discussed earlier what atoms do you have, neodymium ion, and they design the gain spectrum. Right? But the FSR we know is designed by geometrically by the size of the cavity in a semiconductor laser, or by the mirror size and reflectivities and all that. And the so let's look at a little bit about the shaping of the electromagnetic field. Yeah? And again, I'll say that we are talking a bit. It's a survey of a couple of topics in chapter 12 of your book, not going too deep into any one of them, but just a survey of a few topics in chapter 12. And it says advanced topics, but really it is a topic to design the flow of light inside materials. There's another course, at least in ECE, where it's on optical waveguides, where you go into far more details into molding the flow of light inside materials. Here we're going to just do a few survey, but specifically aimed at a laser. Right? What are the designs rules that you need for a laser? Okay. So I will start by just showing a very basic idea of the waveguiding. I've briefly mentioned this a couple of times earlier, but essentially in the laser you have a p-n junction, you have an active region, which is this stripe here, and you're injecting current to push the quasi-Fermi levels Fn and Fp to get gain. And when you inject current, the gain is only in the region that current is flowing. Outside the region where you are not injecting any carriers, that is still a lost region. It's just absorbing. There's no gain in those regions, right? Because your quasi-Fermi levels are still very far from the band edges. You have not achieved population inversion outside here because there are no electrons flowing into those regions. So the current flows. It spreads a little bit. If you don't confine it, it will spread a little bit because of just Ohm's law sort of resistance spreading, and then you get a gain in a restricted window of this material. Now, in the medium then, because you have gain and you have electrons and holes, now you have recombination and photons are generated. And these photons start moving around, and they want to go every which way. They want to go that way, that way. They also want to go sideways, right? And but then you can shape, or you can direct the motion of these photons by playing with the refractive indices of the material. So in a semiconductor, typically what we are using is this active region, which is a thickness of d, which is that one here. That is a smaller bandgap material, so it has a higher refractive index. This is refractive index plot. Refractive index within this region is slightly higher than the larger bandgap regions here and here. This is the double heterostructure sort of laser, and therefore because of this mismatch in refractive index, the electric field of the light wave or the photon wave is going to be shaped by it, by the refractive index. Okay. And this problem is very similar. It's a classical problem. If you have a difference in refractive indexes, how does light flow, right? And that's a classical problem, a classical electromagnetic theory problem. But it's exactly analogous to the particle in a box problem in quantum mechanics. Is exactly the same problem, really, right? So what will happen is light wants to be its electrons want to be in a region of very small potential, whereas light wants to be in a region of a high refractive index. And we'll just briefly see that the equation is, Maxwell's equation is very similar to the Schrodinger equation here. Essentially, the light wants to be here, but then a part of it will leak out. There will be evanescent tails outside in the lower refractive index regions. We'll see that here it behaves as a sine. This is a field, electric field profile. Square of it is the intensity of light. So the electric field here, the profile will go as a sine or a cosine, whereas outside here will be an exponentially decaying function. So that's the same deal as electrons in a so because the form of the equation is exactly the same. But from here, importantly, what you can get is a bound on the refractive indices, essentially that all you will get is as long as N1 and N5, this is historical regions 1, 3, and 5, but refractive indices of outside regions, as long as they are smaller than the refractive index of the internal region, you will get waveguiding, meaning the light would be guided in this direction instead of going out that way and that way. It will be guided along that direction. And that's what you want for an edge emitting laser. And then that's how you shape the a rudimentary way of shaping the flow of light to get it to go in the directions you want, such that they hit the mirror and get reflected and you get gain again. So, or rather you get lasing. I mean, gain you can get by injection of current, but lasing needs feedback. So that's the mirrors give you the feedback. So if I were to just write down the electromagnetic, Maxwell's equations for flow for any electromagnetic phenomena looks like this, right? Is equal to 0 as long as there's no source term here. We will come to that later. Okay, so this is for a region where there are no source terms, an electric field, and similar equation for a magnetic field. You have a spatial Laplace or a double derivative, and you have a time or a temporal double derivative, right? And in general, what we say is for wave equations, we can write it as a function of space and time as an amplitude. Let's put in a direction, some direction it's going in, say k hat, and an amplitude of the electric field, and then it goes as e to the power minus j, beta z minus omega t, where omega is the frequency of the electromagnetic wave. And then what we are going to say is this is the amplitude, but the shape of the electric field in this x, y, and z sort of directions is captured by this function here. This function, that's what captures the shape of the electric field in the x, y, and z plane. This is very similar to what we had done in the beginning of the course for Gaussian beams. I mean, if you go back and check. So we just take this and plug it back in there. And what this time derivative term does is it pulls out the 2 j omegas to the front. It gives you a minus omega squared. And what the spatial derivative here does, so our wave is propagating along the z direction. In other words, okay, that's not good. Okay, so yeah, z is out of the plane here, so it's going along a stripe out of the plane in this picture. So and the spatial derivative for z gives you 2 factors of this. Essentially, I'm saying that if I take this and plug it in here, and I get an equation in this psi, okay, the shape of the electric field, and the equation looks, there after a few cancellations in the spirit of this survey at this point, it looks. Let's write it as omega, which is the frequency over c whole squared. And then there's a refractive index squared as a function of xy. Okay, so minus, and this is beta squared. Okay, this is how, basically it's saying that if you assume an electric field of this form, to solve Maxwell's equations in this laser waveguide, which is propagating along the z direction, you must satisfy this equation now. Right? And this is essentially just the shape of the electric field. And what we looking at this equation, you see that it has 2 derivatives in x, and then you have the same function and some something that looks like very much like an oscillator equation. It's a very much like an equation that looks like d2 of some function over dx squared plus some, let's say, frequency squared f omega squared f is equal to 0, something like that. Okay, and then that's an oscillator equation, right? So it has solutions that depend on the sign of whatever is sitting here. If this quantity here is, if this is, let me write it this way. Okay. This factor, if that is positive, this quantity is positive, then you get an equation which the double derivative of the function is equal to some negative number times the function itself, and it's e to the power j omega t sort of oscillation, or a sine or a cosine sort of function, right? Right away from there. If this thing is positive, you get a psi is, I'm going to write it as approximately as sine of, let's call this as some lambda squared, let's say. Okay. This quantity is lambda squared. So you get plus b of cosine of that same thing, something like that. Whereas if this thing is negative, then take it to the other side, becomes positive, you get a cosine hyperbolic or sine hyperbolics. So that psi would look like maybe like c e to the power gamma x plus d e to the power minus gamma x, something like that. So essentially what we are saying is, if the refractive index here, that's what controls it. As long as the refractive index is, or in other words, the beta, which is the wave vector 2 pi by the wavelength. If beta is larger than refractive index, then you have a certain way of solution. Yep.
Beta is kind of the wave number?
The beta is always the wave number. That's right. Yes.
So that's something divided as k. No.
Yes. So.
Why dividing as beta?
To be consistent with the textbook at this point, but it's interchangeable. Basically, you can use it as k, but generally what's written as k is sometimes written as j, or rather it's beta plus there's a real and imaginary part of it. The imaginary part. So just at this point, do not consider that part. It's
that kappa though.
What's that?
The one with the imaginary part is kappa.
Yeah, that's a notation, but yeah, the imaginary part of it is what leads to absorption and emission and all that. So, but here is just the real part, 2 pi by wavelength. As long as the light is below the band gap, it's not absorbing and all that. Okay. So this is just to show that if your refractive index, the refractive index controls what shape does the electric field take along this direction, which is perpendicular, which is the x direction here. So if refractive index is large, then and this term overwhelms that term, you have a sine term like this, and therefore the electromagnetic field looks like a sine or a cosine term. And then outside, if refractive index becomes smaller, this term becomes smaller than that, then you get exponential decay outside, so the tails, right? And the length scale of these tails are of the order of the wavelength of the light itself. So it's not, for electrons you can cut it off within 1 angstrom or 2 angstroms, but for light it is a fraction of the wavelength. So it's about 100 nanometer or 50 nanometer, depends on the wavelength of light. But physically it's very similar to the ground state of a electron in a quantum well that we talked about earlier. So the shape of it. Yeah. Okay. So this way you can guide the light because of this region. Essentially, the light gets confined more in this direction, and then it kind of moves along the length of the stripe here, for example. Okay, so the second thing that happens is as the light moves along the stripe in the z direction, there are some tails. I mean, these are the two tails of the light wave, which are in regions where there may be many carriers. There are electrons here, perhaps holes here, n and p regions. And so as a result of interaction of these photons, which are outside this active region with the matter there, which electrons or holes or free carriers, there are some delays associated with it. Essentially, you have gain within this region, but outside here, outside the stripes, you have some loss. And as a result of that, what happens is the gain spectrum, as you inject carriers, you have gain within this region. And here's the gain spectrum, but then the gain, because the gain is proportional, if you go back and look at the gain spectrum as a function of frequency, you have a bunch of stuff sitting with the joint density of states and all that, but then you have your Fc of E2 minus Fv of E1, right? And this is really directly, it is very proportional to the amount of injected current you push into this material. Right? So the current is primarily flowing between the stripe and the contact underneath, so it doesn't flow very far out this way, so it just goes almost vertically and then a little bit leak to the side here. And as a result, the gain also kind of takes the shape of the current spectrum, and therefore the gain is large at the, under the stripe, but as you move away it gets low, and then you have loss outside it, because there's no current flowing. This term is negative there, so you have loss. So the gain, as a result, what happens is the light wave that's propagating is seeing kind of a non-uniform gain profile within this region, and as it moves, the phase front, which is going back to your ABCD sort of picture, the phase front is not quite, when it's moving in this direction, the phase becomes curved. In the wings here, the phase lags a little bit, whereas in the top it actually leads, the phase leads, and therefore this is an equiphase surface, so you kind of have a curved profile, and therefore this essentially is very similar to your ABCD beam curvature. If you remember the phase curvature in the top, it's very similar to that. In fact, that's in your book, in this chapter at least, they connect it to the ABCD parameters. You can use ABCD parameters to calculate the phase front of a semiconductor edge emitting laser as well. And then this thing is called, in laser parlance, very similar to eye surgery, and it's called astigmatism. Basically, just that you cannot focus on one point at any time because it's out of phase, the equiphase. So it's called the astigmatism of a semiconductor laser, for example. And then once you come out, the light actually spreads, because outside there is no dielectric waveguiding, so you kind of spread out more in this direction because of this uncertainty principle. But essentially the curvature is due to this non-uniform gain profile. The second thing is this gain region is a very interesting, also it guides the electromagnetic wave. The light will go in regions where there is gain and will not go in regions where there is no gain. Or in other words, if light escapes into regions where there's no gain, it's going to basically it will not come back. It will not be regenerated. It will be lost forever. So this mechanism is also called gain guiding. Essentially, you can guide the light with regions which have gain. So for example, on the top of a wafer, if you want your light to kind of go in like this way, you can put down a strip or contact and inject current, in that direction, and the light will kind of flow that way, because this is called gain guiding. And in a laser, essentially you form a long strip. But as you inject more current, what happens is the current kind of starts spreading out a little bit further out, and so the beam also spreads out a little bit. So as you inject more current, the shape of the beam changes, and then this is one of the undesirable features of a gain guided laser, because essentially if you don't confine the light in the lateral direction, the beam will start kind of becoming broader as you inject more current, because the current is spreading out, the gain region is increasing in size. That is solved by what's called index guided lasers, where essentially what you do is you kind of etch down here, and then you grow another region on the side, regrow another region on the side with different refractive index, so that you confine the light again in that direction. Those are much more expensive because it involves a lot more processing and regrowth and all that, but highly desirable for extremely precise lasers which do not waver when you inject more current. So that's pretty useful, called index guided, but the more simpler version is the gain guided lasers. Yeah. Let me see, what else do I want to mention here? Okay, so that's the point I wanted to get across. Are there any questions? I think I'm going through a little bit on a survey mode now, but this is a very important feature, and based on all that we have talked about in the course, it should hopefully make sense, based on the principles we have discussed in this course. Okay, so the next topic is design of mirrors, and we had discussed earlier that you can take a semiconductor block and you can kind of cleave a facet of it. It's a crystal, so it can cleave along an atomically smooth plane, and then you can have reflection from this difference in the refractive index N1 and N2 being air, so you can have difference of refractive index. But then I think you also know that for a semiconductor, the maximum reflectivity you can get out of here is roughly 30%, because the refractive indices are typically like 2 or 3 max, not max, but that order, 2 to 3. and air is 1, so you get N1 minus N2 by N1 plus N2 squared, reflectivity of 30%, kind of roughly. But that's a etched facet mirror, but you can do actually much better. You can use what's called a distributed Bragg reflector, which is essentially a periodic grating of different refractive indices, N1, N2, N1, N2. It repeats, and by carefully choosing the thicknesses of this N1 and N2, and I'll just briefly discuss that, what is the choice window that you have here. By carefully choosing them, if you have light going through, every time there's a mismatch in refractive index, there's a little bit of a reflection. Now this mismatch may be very small. It can be even 1%. This region could have a refractive index of 3.1, and this could have region 3.0. So I mean, or even smaller than that. But by repeating the periods many times, you can get close to 100% reflectivity you go from 30% here to 100% there. You can reflect it by designing, giving it enough number of periods. You can do it either in a vertical geometry, in a VCSEL, or you can do it laterally in a edge-emitting laser as well by just etching a grating like this. You etch a grating on the side, so you have a laser region, you have these gratings on the two sides, and that's what's going to reflect it back. This is a DBR, or distributed Bragg reflector. The reflectivity spectra of this Bragg reflector, it's not a mirror for all wavelengths. It's a mirror only for specific wavelength. It has a reflectivity band, a band over which it reflects very highly. But if you go outside that band, it can transmit almost 100% if you just go outside of it. So essentially, you want to choose a laser wavelength somewhere inside here so that you make use of the 100% reflection that you have designed it for. So this plot here, which is the reflectivity of a DBR like this or like that, is turned upside down and plotted here. And here's your reflectivity, which is unity if you might, and here's a gain spectrum. So you want to select a mode that's right at the middle of this window over which you are getting the reflectivity, where light is getting reflected. The reason you are using the DBR mirror is to reflect light back into the gain medium again to give the feedback. Right? And you're doing much better now than your just etched facet where you get 30%. Right? So both in plane and a VCSEL, you can use them in both, and they are used in both in commercial devices today. Right? Just as a quick again. Estimate of how do you get this large reflectivity. This is actually a very classical problem almost in electromagnetic theory, where if you have a light wave going through and you have a refractive index mismatch, every time there's a mismatch, there's a little bit of reflection, and then there's transmission, reflection, transmission, and so on. And if your period here is, say, some quantity lambda, spatial period or distance, and your refractive indices N1 and N2. So essentially, if you track the electric field that is formed here due to reflections, because of the first reflection, you get, let's say, electric field that was incident had an amplitude E0, and so you essentially add up all the amplitudes of electric field. You get one reflection with minus J, 2 beta. This is the beta is 2 pi by wavelength again, and then you have two from here, and then from here 2 reflections, beta times 2 this, plus essentially you get this 4, and you get a geometric series, 3, 4. So essentially this distance has 0, then 1, 2, 3, 4, and so on. You get this electric field amplitude that looks like this. I think you know that if you reflect all of them and you add them just in phase, then you get a huge reflection, right? And this is a unique property of waves, not so much of classical particles, but as long as you have waves, you can reflect, and you can have a certain condition under which you have coherent reflection, and all the reflections essentially add up, and there's nothing transmitted. So you can always do that in a wave, and that's because your whole electric field amplitude, you can do the geometric sum here, would look like 1 minus e to the power, if you have n such periods, j n times beta times this whole quantity over beta this. So you get like a sinc function, and if you choose your the thickness, which is if j beta times this is 2 pi times an integer, then you get coherent reflections, and then this essentially means that your thickness should be lambda by 2 of the light times an integer, right? And then essentially, as long as you meet this criteria, within a few periods, maybe 10 or 15 periods, you can recover 100% reflection. Yep.
But so light comes, right, and there's always going to be some transmission and some reflection, right?
Yes. So
But
each.
then, for example, when you reflect on the second wall,
Yeah.
it's going to reflect and then it's going to reflect back, right?
Yes, absolutely. So essentially, it's going to reflect back, and you can continue adding those things as well.
Okay.
So absolutely. I mean, yes. In fact, if you go back and look at our cavity problem, when we studied the cavity, we kind of took that into account. So I'm kind of saying it's the same problem, really, except now you have a periodic cavity where you have a periodic array of mirrors rather than just one. Except the difference is each mirror has a very small reflectivity, maybe 0.01 even, very small reflectivity. And then by putting enough of them in a periodic array, you can get back 100% reflectivity over a small window. That's the message here. And that's the distributed Bragg reflector. Okay, so quite a bit of design goes into this, choosing the right refractive indices and choosing the right thicknesses. But as long as you meet the criteria, you can get a narrow band over which you get 100% reflectivity, and then that's a great mirror for on-chip direct integration on chip. Okay, so now if you can do that, you can actually do a lot of very interesting things. For example, you can take a laser which is emitting, let's say at 30 nanometer. These are communication lasers, like the lasers that feed in photons into optical fibers, close to 1.55 micron or 50 nanometers, close to that. We can start with that, and you can put a DBR on the side, where this is the DBR that is kind of you have etched down and you have created a grating, and the light goes out and gets reflected, right? But the DBR itself, you can actually change the refractive indices N1 and N2 by injecting a separate current into that. You can change the refractive indices N1 and N2 of this DBR region. So that's a separate injection current than the laser, which is giving you your gain and all that. But this is mirror. What you're doing by changing the refractive indices N1 and N2 of this DBR is you are shifting the center frequency of this. You're changing the wavelength over which it reflects. You're tuning it. Basically, you make a tunable mirror. It's a tunable mirror where the reflectivity wavelengths or frequencies over which it reflects 100% is now tunable. So essentially, you're moving this spectrum to the left or to the right here now. So you can select out different modes of the laser now, right? And that's called a tunable laser. And here's an example of so essentially, when you inject different amounts of tuning current, your laser is lasing at 1529. It switches to 1528, 27. So you can, by injecting different currents. And this is extremely useful for what's called wavelength division multiplexing, or WDM, where you have, essentially here, for example, I can have 15 channels of information transfer, and each is at a different wavelength. So you can do that now by tuning the mirror wavelength now. Yeah. The other thing, once you combine them and take it into a system sort of picture, today what is used is multiple channels. So essentially, you'll have many lasers, maybe 40 lasers here, each operating at 40 gigabit per second. They're feeding in information, and then you feed it into optical fiber, and there are different wavelengths. Maybe this one is at 15, here, and another one is there. So you have all these different lasers that are feeding in signal to the optical fiber. All of them kind of are operating slightly different injection currents or such things, and it goes into the fiber, and then you have all this signal going in optical fiber, and the photons are going across, and they don't talk to each other because the fiber is linear, and it doesn't let them talk to each other. They go separately as different lanes in a highway, for example. And then when you receive them, you have a semiconductor optical amplifier, which is essentially a laser again without the cavity, without the mirrors. So it just has gain. You just regenerate the photons. And then you feed it into a photodetector array, again 40 maybe, and each photodetector is tuned to the wavelength that's come in. For example, one photodetector tuned to that wavelength, one to that, and you get this huge amount of data transfer this way. So this is an optical communication system. We have transmit module is based on lasers, and receive module is based on photodetectors, and the channel is based on optical fiber with some gain elements like SOAs, which is a semiconductor optical amplifier. This is a communication system for using light. And it's heavily used. I think a large chunk of emails we sent and online transactions are done this way today. But as you know, it's never enough. This is not enough. I mean, still today we can't stream a movie real time while I'm walking on the street with the phone, right? It's possible, but still we can't do it because there are limitations to the speeds and number of channels you can multiplex and all that sort of thing. So, okay, so the last thing I want to talk about in the application arena is we talked about how do you increase the output power of a laser, but what we did was kind of not quite fair. Basically, what we said is I'm not going to let the laser operate continuous wave. I'm going to do some time domain analysis. I'll basically do mode locking. I'll do all these things. Essentially, we didn't talk about how to increase the CW or continuous wave output power of a laser. We talked about we do mode locking or other techniques where you get large amounts of power but very short amount of time. Right? One way, and that's really because of inherent limitations of each laser. For example, each semiconductor laser diode would output probably a few tens of milliwatts or maybe 100 milliwatt. But then you can always take many of them and have an array of them and you combine them now. Right? Now the combining of the output of many laser arrays is not a trivial task because each laser has its own coherence, own phase, and all that sort of thing. But the problem is very similar to what you call is power combining of an antenna. So because lasers really came from the idea of lasers came from microwave electronics, where you have a lot of say metal arrays. These used to be the old TV antennas, and then you feed into each of them an AC signal, and then you create a radiation pattern. So let's say this array of antennas is going to radiate primarily in that direction. And then you'll have a little lobe here and there and all that, so but it'll primarily radiate in that direction. By changing the phases of these antennas, the currents that you feed into these antennas, you can beam steer it, you can turn it around, and then all that. That's what is used in radar detectors today, looking for enemy aircraft or some stuff from space or whatever, right? So these are used for. These are in a microwave domain where you have individual metal arrays of antennas. Sometimes also these days transistors are used here for transistor microwave amplifiers, and you can create radar arrays like that. But for lasers, it's slightly different because the photons here need to become coherent with the photons there, and that's not a trivial task. These are like a lot of coupled oscillators here. And the way it's done, and this you can buy in the market today. Here's a company product, LaserTel, that takes an array of 1, 2, 3, 4, I don't know, maybe about 10 lasers side by side. And you take the light output from the, it's called a broad area laser diode array, balled array of many lasers. And you take the light out, and you very cleverly, what you do is take the light out from one, and you kind of do mirrors and gratings and reflect it back, and you feed in the light from one to the other and so on. So you kind of combine them such that they end up locking completely their phase. All the phases of each individual laser starts locking into the other. And then by combining many of these laser diode separate emissions, you can get one center frequency, one laser with roughly equal to the sum of all the outputs. I mean, it's not exactly, you always lose some in this process, but you can combine them. So you get a module now with much higher CW power, which has perhaps 8 or 10 of these lasers in an array. Right? But you can do that. I mean, these were a challenge, but now you can people have developed techniques to or optics to develop to be able to power combine on a small enough module. I mean, it's not on chip, but it's somewhat large. So yeah. The optics is large. The laser itself is very small. So, yeah. Okay, so that's for increasing the amount of power. Okay, so that's the end of my survey of chapter 12, which is the waveguiding and how do you take it towards applications. So what I want to do for the last 5 minutes today and the next class is talk very briefly about two things which we have kind of accepted ad hoc, or we didn't try to ask very deep questions about the heart of the physics of semiconductor lasers, and that is the Einstein A and B coefficients. So we said that in an Einstein A coefficient in any laser, or any optical system for that matter, if I have N2 atoms sitting in an excited state, I have an Einstein A coefficient that looks like that, right? It's telling me how fast will these atoms decay, right? It's the rate of decay. And then I have the B coefficients, N2, and then you have the photon field, and then you have a B coefficient for absorption, and 1 times the photon field, and something like that. So we have earlier part in all our discussions till now, we have said that the A and the B are related. We know the ratio A by B, is related to wavelength and 8 pi h bar and all that. But what is A? We said we can measure it experimentally. You did in your lab assignment, right? But how do you get it kind of from first principles, from either classical mechanics or from quantum mechanics? Can you get A? And the surprising thing is we'll see that you can get A, the Einstein A coefficient, relatively easily by classical mechanics. I'll just show that in a classical electromagnetic theory, not classical mechanics, but classical electromagnetic theory. But the A coefficient is extremely difficult to get by quantum mechanics till you go into what's called quantum electrodynamics, where the electromagnetic field has to be also quantized, not just the atoms and all that. On the other hand, we'll see that from I'll give you just the kind of a survey sort of summary. The B coefficient is very easy to get from relatively easy to get from quantum mechanics, but kind of hard to get by classical mechanics in some sense. And then we'll see the A coefficient first from classical electromagnetic theory, and that actually takes not much work to show. So let me just talk about the Einstein A coefficient from classical electromagnetic theory. The picture is the following. So we look at an atom as you have an electron and you have the nucleus, and the nucleus has a very heavy mass, the electron has a small mass, and the electron is obviously attracted by Coulomb attraction to the nucleus. So we can imagine there's a little spring connecting to the electron to the nucleus of the atom, and there is a certain Bohr radius, or the certain equilibrium distance that the electron maintains from the nucleus center. And then if I kind of tweak it a little bit, for example, there's an electromagnetic wave that comes in and it sloshes this a little bit, right? The electron goes this way, but then it says, oh, I'm out of equilibrium, comes back, and it starts doing oscillations around this because it's a mass spring system, right? And he asked, can I do some quantitative analysis of that? Let's say the amplitude over which it oscillates is delta x naught, which is the perturbation or rather let's call it that 2 times delta x naught, meaning the amplitude is x naught, it can go plus or minus delta x naught. And it's a mass spring system. So we can write that if it gets displaced by a certain distance, delta x, at time t, and this is changing with time because it's oscillating like that, right? So we can say that this is how far it is from its equilibrium position at time t. And now the electron charge times this distance, which is a displacement from its equilibrium position, minus E times that, is what is defined as the polarization of any material system. Polarization is basically it's a dipole, it's formed a dipole. It's electron charge, it's the charge on the dipole times the distance they're separated by. This is the dipole, or it's a polarization. Let me not worry about vectors and all that, it's going in some direction. This is the polarization, and because of this you get a current, which is rate of change of the polarization. That's the current that flows. Now, because it's an oscillator, I'm going to make an assumption here that it has this amplitude, and the frequency dependence or the time dependence goes as, let's call it sine of omega 21 t, where omega 21 is a certain characteristic frequency for these oscillations. It's basically similar to if you have spring constant k, mass m, omega would be kind of spring constant by mass, kind of that thing, right? Roughly, or this is the classical mass spring system would oscillate like that. And the rate of change of the polarization is is therefore given by a time derivative of this quantity that just happens to be delta x naught. When you take a time derivative, the omega comes out of the sign, and you get a omega 2 1 times cosine of omega 2 1 t. Right. So that's the rate of change of polarization in this material, in this atom system, with the electron kind of sloshing around a little bit. Right? And now, whenever you have such a situation that a charge is oscillating in space, it's going to radiate power. Right? This is a classical electromagnetic phenomena. You can go back to what's called Larmor frequency, or all these other things. But whenever a charge oscillates in space, it's radiating electromagnetic power. Right? And that's the basis of all antennas, including the antennas on our cell phones. We have metal, and we oscillate the charge at a gigahertz. It's going to radiate electromagnetic power at a gigahertz. And so I will kind of leave it here. There's a simplest expression to calculate how much power is radiated by such an element. Is given by the following. And let me just write it down, and we can end the class today here. So if I take a very small metal wire like that, and I connect to it an AC signal which is driving current at cosine omega t, let's say, right? Then because the charge is sloshing back and forth, between this to that in half cycle, it radiates power, and the power radiated. Power is radiated as electromagnetic wave, so maybe magnetic field coming out, electric field going that way, E cross H, so power goes out. And so the power radiated by such a oscillator, or a Hertzian dipole if you might, is given by this formula, and this is a derived way before quantum mechanics and all that. It's given by 1/3 pi times the impedance of free space times I naught, which is the current amplitude that's driving it, squared times, let's call it, this is delta x naught, the distance of or the length of the dipole over the wavelength which is emitted, squared. That's the formula for output power of any dipole. And this is, if you have taken an EMAC course where you get to antennas or radiation power from dipole, this is output power from a dipole. So let's end it here. What we'll do in the next class is show that from here, and by looking at the atom, we can get a classical expression for the Einstein A coefficient right away, in a couple of steps. And then we try to make it a little more accurate, go towards quantum, and that will open up a whole can of worms saying we don't know this, we don't know that. And that will be a good place to end the course, I think. So, okay, good. So let's meet on Wednesday. Those who have not picked, so the assignment 5 graded is here. Please pick them up. And please start working on your lab 2, and approach Professor Pollock to design the laser.